All right, our last speaker on the topic of habitability today will be Danica Adams, and she'll be speaking on the chemistry and climate impact of sulfuric acid hazes on early Venus. Go ahead and take it away when you're ready.
Hello, can you hear me? Hooray. I'm Danica. I'm a postdoc and I like Venus, so let's talk about it. Cool, thank you. So a few years ago, there was a paper that argued that Venus was always hot right after it formed. It's likely that early Venus experienced a steamy atmosphere, especially when it had a magma ocean, because the atmosphere would have been in equilibrium exchanging between the atmosphere and the surface. So in that steamy atmosphere, this paper from a few years ago argued that water vapor on the day side would absorb photons and keep you warm. And on the night side, you might form water clouds, which would also help heat the atmosphere and keep the planet very warm. And so the hypothesis was that Venus has been hot almost always. Now, Venus is hot today, but when we look up in the night sky, Venus also looks very bright and shiny. This is because of sulfuric acid aerosols that reflect sunlight off of the atmosphere. So it's possible that these aerosols could have also formed at early Venus, and maybe at different rates. So the goal of my work is to see if these aerosols could have formed in a way that could have cooled off early Venus at some point in its history. So to do that, I used a photochemical model. The model assumes that you must have SO2 in the dry troposphere, and that SO2 can transport up and down along with all the other gaseous species in the model. The SO2 can also get hit by sunlight and form some reduced species like SO and S, and ultimately form maybe S8. But Venus's atmosphere is very oxidizing. So more often, SO2 will get oxidized either through O or OH. At Venus today, O is more favorable. And ultimately, it will form H2SO4. H2SO4 can cross a condensation vapor curve line to form droplets and ultimately find hazes up in the upper atmosphere. Now, if Venus ever was cool at some point, then maybe it could have had a moist troposphere. Here you could also form water clouds where your SO2 could dissolve into the droplets and fall to the surface or to the lower atmosphere. If it was cool, it's possible the SO2 could have been cold trapped, or maybe not all of the SO2 would dissolve and more would transport and be available for hazes. So the first question we have to answer is whether the SO2 gets cold trapped in a moist troposphere in a kind of cooler atmosphere. So to do that, I used a box model just in Python. And we said that the SO2 as a gas could either transport up and down, or it could dissolve into a droplet. And that dissolution would be in equilibrium according to the Henry's law's constants. Once it oxidized to S4, it could either rain out, or it could continue to oxidize all the way to S6 before it rained out. So this process is pH dependent, and we assumed that only H2SO4 was affecting the pH. But if you do include maybe a strong number of bases, that could modify your result. What we found is that the SO2 generally does not get cold trapped if you have a moist troposphere layer. So in this plot, we assumed that there was 10 ppm of SO2 near the base. And then we're watching the SO2 kind of transport through that cloud layer. We did it over a range of eddy diffusions and also oxidation timescales. And you can see that most of the plot has 10 ppm SO2 reaching the stratosphere. So very little got dissolved and cold trapped into the droplet. There is a small region on the plot that's not yellow, and here about half or maybe even 2/3 of our SO2 is getting cold trapped, but that still means that a large fraction is available to form hazes. So from this result, we prescribed a rate coefficient for that loss and then stuck that into our photochemical model. So our photochemical model is solving to steady state the mixing ratios of all the gases. And then I've modified it to also consider the rate of haze formation. So in order to form a haze, the H2SO4, the yellow line, has to cross the saturation vapor pressure line, which is the gray line. And the left panel here is showing a Venus-like atmosphere that's very dry, but we ran this over a large range of cases, varying both the surface temperature and water vapor. So from left to right, we're increasing the amount of water vapor in the atmosphere. But starting with just the Venus case, this is the mixing ratios versus pressure. So it's a profile. And you do form haze at Venus, which is great because we see hazes today, where that orange line is crossing the gray line. Now, as you add more water vapor into the atmosphere, the water can supply more Hawks. So that allows you to oxidize your SO2 faster and to form hazes faster. So here the orange line is still crossing the gray line, and if you were to integrate that rate over the profile, it's a little faster than at present day Venus. But in the case that's very steamy, notice now that the gray line has shifted to the right. This is because the mean molecular weight of the atmosphere has decreased. Water vapor is lighter than CO2. So this made the scale height larger, the atmosphere looks puffier, and so your temperature profile has been pushed up, and your vapor pressure line got pushed to the right. So now it's very hard to cross it. So even though you could form H2SO4 if photolysis had been shielded, now you can't form haze because that line got pushed, and so you're not shielding your H2SO4 from photolysis. So most of the profiles get swooped to the back because of that photolysis, and you don't form haze in the very, very steamy atmospheres. So we ran this over a range of cases. These are just 3 examples. In the next plot, I'm going to collapse, thank you, each plot to a single dot on a grid. So the hazes would loosely track with the albedo after you solve a climate model. So here I'm showing the albedo that pops out of our photochemical model versus the amount of water and the surface temperature. So when Venus had a lot of water vapor, when it was very steamy early on, we find very dark albedos because you couldn't cross that condensation curve line. But then as Venus would have lost its water vapor through time, the albedo experiences a sharp increase from very dark to very, very bright. This is again because in that intermediate place of about 10% water, you had just the right number of oxidants to help oxidize your SO2 faster to form haze, but your mean molecular weight is just right that you're able to also cross that condensation curve line. So in this case, where the albedo is greater than 0.9, our climate model expects that early Venus would have had a very strong cooling effect in the climate. And so as Venus lost its water through time, this plot says that you would move up on the plot once it's blue and it's cooling off. It would go so far up that you would reach the spot that's intentionally blank. In that blank spot, Venus is now experiencing rain to the surface. This is tricky because we can't test our hypothesis. Venus's surface is very young compared to, for example, Mars. And so we encourage folks, possibly with the Hab Worlds Observatory, to try to study exovenuses to test the idea that maybe early Venus could have been cooled off by thick hazes. But then as it continues to lose its water vapor, the number of oxidants is now decreasing, and the haze formation rate slows a little bit, and you end up in a spot where you're heating up again, and the albedo matches the present-day Venus albedo near 0.7. So just to recap, we predict that Venus's atmosphere could have been cooled off by sulfuric acid hazes when it had between 6 and 12% water vapor. And this cartoon shows our predicted kind of evolution track of Venus, where it would have started with a very steamy atmosphere, lost some water and cooled off abruptly to the point that maybe it had a thin film of liquid water on the ground that's very acidic. But then as it loses more water vapor, the rate of haze formation slows and it heats back up to land at present-day Venus today. So that's all I've got, and I'm eager to take questions. Thank you.
Questions for our speaker?
Thanks, Danica. I have a question about the HWO tie-in. Could you say a little bit more about that? And specifically, are you thinking about spectral signatures of these worlds, and are you also thinking about if you had a population of kind of inner edge worlds, trends that you would be looking for?
Yeah, I think something interesting is that in this region of the plot, you might expect to see SO2 and water vapor, but not haze. Whereas previous works, a lot of them thought you would just see a lot of haze if you had SO2, where you would expect to see really bright hazes here. So maybe in this spot, you would be trying to track albedo changes, but in this spot, you would expect to see those spectral signatures. Thanks.
Hi, this was a very interesting talk. Thank you. Did your model, did you see any changes in like the haze parameters given these different initial conditions? Did they get bigger or smaller, anything like that?
Haze parameters like the thickness or like the optical properties?
I guess I meant more like physical parameters of the hazes, but whatever works, I guess.
Yeah, thank you. So we've assumed like a certain particle size, so that by definition is not allowed to change. And we're also assuming just sulfuric acid, probably not the best assumption because Venus's hazes are kind of mucky. So all we're tracking here is just how the haze thickness changes, and that's really what's driving this change. But that would be interesting to test because we know Venus's haze today has some muck in it, so we should probably turn that knob of like single scatter and albedo. Good question.
All right, that's all our time for questions. Let's thank Danica and all of the speakers in our habitability session.